Hello, this is Professor Dan Kernler of Elgin Community College again. This is another video in my statistics series. This one is all about probability. All right, let's get to it. We're going to start this video just by talking about some vocabulary. First thing is a probability experiment. In this context, that's just any process where the results are uncertain. So like we roll a six-sided die, the results are uncertain. The sample space is all the possible outcomes. So with our example of the six-sided die, that would be all the different six sides of the die. An event is any collection of those outcomes. So for example, if we think of our sample space, we've got these six sides of a single die. If we talk about the event, we roll a 1. Well, that would be a simple outcome, but that's an event. You roll a 1. Different example, maybe we want to know we roll an even number. Well, those three different outcomes constitute a single event. That's an event. It's a collection of outcomes. In terms of calculating probability, the classical, theoretical method would be, well, the probability that event E is the number of ways that event E can occur over the total number of outcomes. And shorthand, you could say capital N of E over the total number in the sample space. And we usually use a capital letter S to represent the sample space. For an empirical method, this would be like if you don't have a theoretical probability and you're just going to look at what happens. This would be if I had a die that I wasn't sure if it was fair. I could just roll it 1,000 times and then count all of those up. So here the probability is about the relative frequency of an event, or it's the frequency over the total number of trials. So you have classical probability, that's just in theory. If you know something about the deck of cards or a flip of a coin or the die, then you can find the probability that way. And then empirical probability would be just looking at data, looking at some kind of tests or trials that were done. We're going to have a variety of probability rules. The first one is the addition rule. So I like to illustrate these with some graphics. So suppose that all the dots in here represent the sample space. And I have some event E, and it's these 4 different dots. And I have some event F, and it's those 5 dots. I want to find the probability of E or F happening, either one. Well, I could find the probability of E and add to that the probability of F, but there's some overlap there in the middle, so I need to subtract that overlap. And this is the addition rule. Now, it's slightly different if your events don't overlap. That's called disjoint or mutually exclusive. In that case, suppose we have an event E and event F, they don't overlap. So if I want to use the addition rule, the problem is there's no overlap. So the probability of E and F both happening is impossible. So you just get a much simpler rule. My recommendation is don't worry about 2 different rules. Just remember the one general rule, and then sometimes your probability of E and F will be 0. Okay, let's talk about a different context here and do an actual example. I'm going to use a deck of cards here. You might be familiar with this. Here's a standard deck of cards where there are 4 different suits. You have spades, hearts, diamonds, clubs, and then you have 13 different ranks. So you have an ace, a 2, a 3, a 4, etc., all the way down to jack, queen, and king. Let's define a couple of events here. Let's define event E. Suppose we randomly draw a card. We kind of shuffle the deck and draw a card. The event E will define to be that the card is a heart. And the second event F will define to be that the card is a face card. So suppose I want to do this addition rule and I want to find the probability of E or F. So that means I want to find the probability that it's a heart or it's a face card. Well, this one's easy enough. You could just count them, right? You just count them up and say, oh, it's 22 of them. So 22 out of 52, that's about 0.423. So that's fine. I just want to use this as a practice to illustrate this addition rule. If we want to do the addition rule, it'd be the probability of E plus the probability of F minus the probability of both E and F. Well, let's think about what those would be. The probability of E, well, that's the 13 hearts. So that's 13 out of 52. The probability of F, that's all of the face cards. There are 12 of those. So that would be 12 out of 52. And then probability of E and F, those are the hearts and face cards. There's 3 of them, so we have to subtract 3 out of 52. And of course, we get the same thing. It's still 22 out of 52, 0.423, etc. The point isn't that this was a better way to do it, but just a way to illustrate this addition rule. And basically, when you're adding probabilities together, you have to remove the overlap because you might have counted the overlap twice. The next rule is the complement rule. The complement here, be careful, notice the spelling. It's not complement with an I, like, wow, your hair looks nice today. No, it's complement with an E. It's like complementary angles from geometry where they kind of match up to give you the total of 90 degrees. Here, the complement and the original event make up the whole sample space. So if I have an event E, then the complement will denote that with E with a superscript of C. That's called the complement of E. That's everything else. There is a probability rule that goes with this. So if we take the probability of an event E and we add to that the probability of the complement, well, that's everything. So we should get 1. That is the complement rule. You add the probability of an event and the complement, you get 1. It doesn't seem particularly helpful when you first look at it, but we actually use this one a lot. It's really helpful when our probabilities get more complex. Let me give you an example. Suppose we have our cards again, and we're going to define an event, and we're going to try to look at the probability that we draw a card at random, and it's not a red jack. So you may already naturally be using the complement rule without even realizing it. Because the way we would do this using our traditional probability rules, we'd have to count them all up. So that means we have to count everything that's not a red jack. So we go, okay, well, that's those 2 left out. So then 1, 2, 3, 4. This is way too much work. Way too much work. Okay, so instead, why don't we look at the red jacks and say, well, there's 2 of those. And why don't I just subtract those from the total? And say, well, I'm going to use the complement rule and say it's 1 minus the probability of a jack. In fact, my notation is a little bit off. There should be probability of a red jack, right? So that would be 2 out of 52. 1 minus 2 out of 52 is, of course, you already knew this, 50 out of 52. That's one of those where if your event is really complex, try looking at the complement. Maybe looking at everything else will be simpler. And that's when we use this typically. If we have a very complicated event, maybe the complement will be better to look at. The next type of probability we're going to investigate is when the probability of an event might depend on what happened in a different event. So let's look at our cards again. Suppose we draw 2 cards this time without replacement. That means we draw a card at random and then we draw a second card. And we want to know what's the probability that if the first card is a heart, then the second card is also a heart. Now, there are 13 hearts, so the probability that a card drawn at random is a heart would be 13 out of 52. And just for the sake of example, let's say we draw the 10. So now the 10 is gone. The probability that the second is a heart would now just be 12, because there's only 12 hearts left, and there's only 51 total cards left. So the probability that the second is a heart, given that we know the first is a heart, would be 12 out of 51. Let's dive a little bit deeper into that probability. The probability that the second is a heart, given that the first was a heart. So if we define 2 events, E is that the first card is a heart, F is that the second card is a heart, this would be the probability that F occurred, given that E has already occurred. We can shorten this notation. We actually put F and then we do a vertical line and then E. That's F given E. That's the probability of F given that E has already occurred. And that is conditional probability. Conditional probability is when you can't find the probability of your event because it depends on another event. Formally, conditional probability is the probability that F occurs given that E has already occurred. Let's illustrate this with some data. Here I have data from our immigrant database. We have children of immigrants, and there's a wide variety of variables in there, but one of them is the mother's education and then also the individual's health. So the child's health. Now the child may not be a child as in 6 years old. They might be an adult, but it's their health and their mother's education. So suppose we select an individual at random from this database, and we want to know what's the probability that that individual has excellent health given that their mother was not a high school graduate. So what that means is we're not just going to find the probability that they have excellent health. We have to limit our sample space, and we're only going to look at the ones that were not a high school graduate. Let's practice some notation here. Let's define event E to be that they have excellent health, and define event F to be that the mother was not a high school graduate. So that means the probability that you have excellent health given that the mother was not a high school graduate means we want to find the probability of E given F. All right, well, let's look at the database here. This is an empirical distribution. We have actual data to look at. And so we're going to make a ratio. We want to look at just those where the mother did not have a high school diploma. She didn't graduate high school. We can look at all of those totals. That's 271 plus 231 plus 355. And then, so that's our denominator. That's the ones that just the mother did not have a high school diploma. And then we want to know the probability that those individuals have excellent health. Well, then we'll look at that column and add up those 101 plus 81 plus 156. And so we find the probability that a randomly selected individual has excellent health, given that their mother did not have a high school diploma, is about 0.394, about 39 hundredths. All right, what about those who have a college degree? We could do similar analysis. This would be the bottom row. The same idea. We'll define event E to be that they have excellent health. F, in this case, is going to be that the mother has a high school or graduated from college. So the probability here would be the probability of E given F. That would be 397 out of 771. So it's a little bit higher at 0.515. We're about 39 hundredths for the previous one. Here we're about 52 hundredths. So about 13 percentage points higher likelihood of having excellent health if the mother has a high school diploma, if the mother has a college degree versus if she did not graduate high school. The next topic is about independence. This is a very specific definition, and this is really important. In a probability context, two events are independent if the occurrence of one event doesn't affect the probability of the other. With probability notation, that would be the probability of E given F is the same as the probability of E. Or you could do vice versa. The probability of F, given that E has occurred, is the same as the probability of F overall. Let's check that with our Children of Immigrants database. We could check to see if two different things are independent. Let's look at the excellent health and college graduate. So the probability that an individual has excellent health, given that the mother was a college graduate, that's about 0.515. If we look at the probability of excellent health overall, that's about 0.454. Those are close, but different. So we could say it looks like they're not independent. I'm kind of fuzzy a little bit here. It looks like they may not be independent because when you have data, those probabilities are never going to be identical. And just because of rounding, you got sample size issues. So these look pretty different. They're about, 6 percentage points different. So that's pretty significant. We will learn actually toward the end of the semester what's a threshold for how different is too different. It's actually called a chi-squared test for independence. So we're going to learn that toward the end of the semester to know how different here is different enough. But following the definition of independence, given the data that we have, they do not appear to be independent because the probability of excellent health given that it's a college graduate is different from the probability of excellent health overall. All right, want to build up to another probability rule. We're going to do a theoretical example here. Suppose I have a $1 bill, another $1 bill, and a $5 bill. And I want to look at what is the probability that the second bill drawn is the $5 bill. We're going to define two events. One is the event E, that the first bill drawn is $1, and then event F is that the second bill drawn is the $5 bill. So what we want to find is the probability that the second is a $5 bill. So that's probability of F. Well, technically, the only way you can get F is if E has occurred. So we really want to find the probability of E and F. Let's list out all the different things that could happen. So I have different colors here, blue for the first one and brown for the second one. So we could have the first dollar bill is blue. The second one is also the other dollar bill. So we could have 1 and 1. We could have 1 and 5. We could switch the order and The second dollar bill is drawn first, and then the first dollar bill. Still, it's the same two bills, but it's a different order. You could have the middle dollar bill and the 5. Then you could have 5 in the first one, and then 5 in the second one. We want the ones that have the $5 bill being drawn second. So that's these two. So it would be 2 out of 6 or 1/3. The probability that the $5 bill is drawn second is 1 out of 3. Okay. What we're going to do is we're going to try to develop a probability rule by investigating this and diving in a little bit deeper and kind of splitting this a little bit differently. So let's just look at those 6 outcomes. We have 4 of them have a $1 bill first. So 4 out of 6 have the $1 bill first. Of those, half, 2 of them, have the $5 bill second. So we need both of those. We need the $1 bill to be first, and then of those, we need the $5 bill to be second. So we're actually multiplying these. We're taking 4/6, and then we're multiplying that by a half. So we really have 2/3 times 1/2. Here's the cool part. Take a look at that 2/3 times 1/2. The 2/3 is the probability of getting a dollar on your first. There are $2 bills, 2 out of 3, 2/3. And then the 1/2 is if the dollar was picked first, then the probability of getting a 5 would be 1 out of 2. So what we're really doing here is we're multiplying the probability of E times the probability of F given E. And that is a rule for how to find the probability of E and F. It's the multiplication rule. So the probability of E and F is the probability that E occurs, and then you multiply that by the probability that F occurs, given that E has already occurred. Let's look at the multiplication rule in an example. Let's go back to our cards, where we have the 52 cards, and suppose we do this draw 2 cards without replacement, and we want to find the probability that they're both hearts. So we can define a couple of events. Let's do event E is that the first is a heart, and then F is the second is a heart, and we want to find the probability of E and F. Using a probability rule, that's the probability of E times the probability of F given E. Well, there are 13 hearts, and so the probability of E will be 13 out of 52. That's the probability of drawing a heart at random. Now, suppose, just for the sake of illustration, say we drew 7. So now 7 is gone. There are 12 left, and there are only 51 cards left. So the probability of F given E is 12 out of 51. Multiply them together, we get about 0.059. So you have about a 6% chance of drawing 2 hearts when you draw 2 cards at random from a deck of 52. All right, that is it for this video. There's a lot of probability rules in this one. I hope you found it helpful. If you want to see more of these, you can subscribe, hit the bell to get notified. And thank you, as always, to the Elgin Community College Board of Trustees for approving my sabbatical during the spring 2021 semester. That's what gave me all the time to do all this recording and editing and producing and uploading these to YouTube to share with you. So thanks again so much for watching, and I will see you in the next one.